In this video, we're going to briefly discuss the history of operating systems. So basically, we started with hardwired computers. From there, we went to mainframe operating systems like OS 360. We have our first mini computer systems like Unix, PCs with MS-DOS, multiprocessor modern OSs like Mac, Windows, Linux. Then we came up with mobile addresses, and now we have special purpose embedded hardware in appliances and cars. Here's an interesting graph of people per computers. Here we have one person, or we'd probably have half a dozen people. Here we'd probably come down to a handful. Here's where we first start seeing one or two, and now it's like in your hand, very tiny. The first major computer was called ENIAC, and it was in 1945, and this is kind of what it looked like, or this is what it looked like, and look at all those punch boards. This thing doesn't even have half the power, or even a quarter or a tenth of the power of your cell phone, or cell phones from 10 years ago for that matter. After that came mainframes, which were often used to batch similar jobs. They sequenced transfer control from one job to another. From a user's point of view, it could be a large amount of time for something to complete, but also there was no protection between two user programs or between user programs and the kernel, which was then called a monitor system. So things could stomp on each other. The typical flow would be from a card reader into the CPU, out to a tape drive, and then to a line printer. So a simple batch system had basically two areas. It had the operating system and the user program area. That was kind of it. No protection. The next step was multi-programming, and it increased CPU utilization by organizing jobs so the CPU is always working. It did require special hardware to protect each job from snooping or stomping on other jobs. So here's be OS, and you'd have job 1, 2, 3, 4, etc. The features needed for multi-programming are memory management. The system must allocate memory to run across several jobs. CPU scheduling. The system must choose among several jobs ready to run, and disk storage. The next step was time-sharing systems, which is a logical extension of multi-programming. It allowed users to share the computer simultaneously. If the response time is quick enough in multi-programming, the user had the impression or the illusion that they had direct access to the computer. It was kind of the first idea of a context switch. Interactive communication between the user and the system is provided. When the operating system finishes the execution of one command, it seeks the next control statement from the user's keyboard. Unix was originally built around time sharing, and it was originally actually called Multics, or actually it came from Multics, and in a insight or a good joke, Unix was a quote-unquote castrated version of Multics. Unix was released 11/3 of 1971, which is 0 day on Unix. It's considered one of the most influential pieces of software ever written. It was created by Ritchie and Thompson at Bell Labs. Ritchie is one of the creators of C. Many popular versions of Unix were BSD, POSIX, Xenix, Mac OS, Solaris, and then came Linux, and almost everything except Mac is now Linux-based, not Unix-based anymore. Linux started out as a free system to be used by universities and such. And when Unix started out that way. When AT&T commercialized it and stopped making it free, Linus Torvalds came up with Linux. Unix let programmers call 34 different low-level routines built into the OS. It was written in C, which was evolved from B, and Kernighan and Ritchie invented it while working on Unix. Nearly all of these system calls are still available and used in modern Unix and Linux 4 decades later. For its time, first edition Unix provided a powerful environment for development, but it contained just 4,200 lines of code at its heart and took 16 kilobytes of main memory. Think about how small that is compared to today. I think the minimum for Windows is what, 8 gig now? Or is it 16? It's 8. Here were some of the people. Linus Torvalds posted to compos.minix. Hello, everybody out there using Minix. I'm doing a free operating system, just a hobby. Minix was in a book by Andrew Tannenbaum, and it was a small operating system based on Unix that could be used by students. Linus Torvalds took that and built it into Linux. What's funny is nowadays Torvalds badmouths Minix. So, personal computer systems were originally a single processor dedicated to a single user, had keyboards, mice, printers, etc. It was focused on user convenience and responsiveness, and adopted technology developed for larger OSs. There are several different types of personal computer OSs: Windows, Mac, Unix, Linux, etc. Early examples were Apple DOS, CP/M, and MS-DOS. The Apple II and Apple DOS. This is what I used when I was in high school. Then we had MS-DOS, which was what came about in 1981. Microsoft released it, and it was kind of the precursor, or it was the base upon which the original Windows was built. It came about because IBM originally wanted to use CP/M to drive their new PCs, but they couldn't negotiate well with Digital Research, which is funny because corporately speaking, it cost Digital Research their corporate life. Bill Gates had learned about the pending PC through family and offered an OS. What he went around and did is bought QDOS, Quick and Dirty DOS, from a small company, renamed it MS-DOS, and licensed it to IBM, who renamed it to PC-DOS while retaining the right to market to others. So that's why back in the early days you saw both PC-DOS and MS-DOS, but they were the same thing. Now in 2016, it's been shown 89% of households had a computer. There's on average multiple CPUs per person, 100 plus maybe. Your car has 50 chips or more. Your phone, your laptop, your home computer, the resources at your university, Amazon, Google's server farms. A data center can be thought of as a single huge computer, and now with the cloud, that's actually even more model used. Computers are everywhere. Multiprocessor systems with more than one CPU in close physical proximity have some different challenges. Increased throughput, you can get economy of scale, increased reliability. You have tightly coupled systems. Processors now share memory and a clock. Communication usually takes place through the shared memory. Multiprocessors don't always have physical processors. They can actually use cores now, which are multiple processors on a same chip. There's two types of multiprocessing, which we'll talk about later: asymmetric or symmetric multiprocessing. Another server is a blade server, which has multiple processor boards, networks, etc., and they're placed in the same chassis. They're basically individual computers placed in a bigger box. So, two cores on the same chip. Here we've got a processor chip. It has its own registers, its own L1 cache, etc., and then there's a level 2 cache that is shared amongst the various processors. Could be more too, and they talk to main memory. Clustered systems allows two or more individual systems to share storage. It provides high availability. Asymmetric clustering is one server runs the application while the other servers stand by. Symmetric clustering is all n hosts are running the application. They have different levels of reliability then. Distributed computation among several different physically separated, possibly of different types, computers, which are networked to provide various resources the system maintains. It basically spreads everything out. This requires networking infrastructure, such as a LAN or wide area network, a WAN. Load balancing is done for high performance and scalability. They tend to be more fault tolerant and highly reliable. Some ideas are client server, peer-to-peer, or web-based systems, also referred to as N-tier systems. So in client-server computing, there's an interface to a client to request services, typically from a database. File servers provide interfaces for clients to store and retrieve files. The biggest thing about client-server systems that's a problem is it doesn't scale well. That means if you have 100 users, you're going to have 100 database connections, and good luck with that because it's probably going to bog down. Peer-to-peer computing doesn't distinguish between clients and servers. All nodes are considered peers, and each may act as a client or a server. A node must join a P2P network, and it registers services with a central lookup on a network or a broadcast request for services and respond to services via a discovery protocol. Napster was a good example, Nutella, and torrents. BitTorrent. A distributed system, another approach, is web-based computing. The web has become ubiquitous. More devices are networked to allow access. New category of devices to manage web traffic are called load balancing. And cloud computing has computing resources that are delivered as a service over a network, and you don't know where they begin and end. They can scale up, scale down, but you don't have to worry about the details. There are special purpose systems as well, real-time systems. They're often used as control devices in dedicated applications such as scientific experiments, medical imaging, and that sort of thing. And they typically have to deal with well-timed, well-defined, and fixed constraints. Now we have also handheld systems, limited memory and CPU speed, PDAs, which have kind of gone out of vogue, cell phones, smartphones, tablets. The two primary OSs there are Android and iOS, because Microsoft's entry kind of died. And the amount of traffic increased on mobile is just going through the roof. So the conclusion is different environments lead to different requirements of operating systems. And if you see, it basically advanced over the course of the last 70 years from just monolithic to much more flexible and smaller operating systems, as well as computing platforms.